it has been estimated that 2060 global energy demand would be double of now. Still, we are lacking of electricity, but in coming futures, energy demand again it is going to be double. So, without alternative fuels or without alternative resources of energy, we cannot handle or we cannot accomplish the demand of energy. CO2 emissions should not exceed the value of 29,000 gigaton up to 2100. In 2014, already we have reached to 1900 gigaton of CO2. This is alarming for us. Similarly, global mean sea level has risen approximately 0.19 meter between 1900 to 2010 with the rate of nearly 1.7 millimeter per year. This is the effect of CO2 emissions and eventually the global warming coming up. Last point I would like to emphasize, that is, if it has been increased 1 meter like that or the 6 meter is like that, then all the coastal flooded, erosion, saltwater, contaminations of the freshwater supplies will increase, and nearly 625 million people residing in low elevation coastal regions, they will in risk and exposures to these hazardness of sea level rise. This is very dangerous conditions we can face in coming up year because of the global warming, and that is only due to our activity where we are emitting this CO2. What is the solution of it? So please tell me if 30 minutes will be there. Okay. Okay. So one thing is that we have the tremendous amount of biomasses are there. These are the different biomass you can see in the slide. Primary biomasses coming up, and secondary biomasses once we are using, thereafter it is no used. Only few percentage is been recycled, but remaining portions is as it is in the earth. So that comes under the secondary wastage of the biomass. So some other facts is there. Government of India, MNRE, is promoting alternate fuels so that the previous the alarming positions could be reduced. And other things are there, that in India, agriculture residues as per hectare 16,423 area is been covered, and 95,512 kiloton per year the biomass is generating, and the surplus biomass we have like this data 43,000. So if you total, if you get it in terms of agriculture residues, forest and wasteland, then this will be million of tons in per year. This means we can surely utilize this biomass so that it could be meet to the energy requirement in certain extent. Potential of biomass energy, it's as abundant. Biomass reduces the dependence on fossil fuels. Okay, these are many advantages already I have told you, but disadvantage is there. The collection of biomass is very difficult because it is in a scattered manner, and a lot of economies is to be waste on that so that this could be collected. This is seasonal based. In the summer season also, in summer season only some few the trees used to be come down from the tree itself. Then from there you can collect it. Some small trees are there that is to be dried, then we can collect it. Some leaves are there that used to come up, and that we can collect it. And from the different industries like wood industries, saw industries, from their wastage are there. But this wastage is also depends on the seasonal basis. So what are the different conversion techniques of the biomass? Well known, the technology, this is called thermochemical technologies, where thermal is there and chemical is also there. Through this we can convert the waste biomass, not a living biomass. Waste biomass we could collect and we can transform into purposeful energy, so that the requirement of fuels or requirements of heat or some power generations could be taken up. So these are the different routes are there. One is called esterification systems or transesterification system. Through this we used to convert the biomass into the liquid form. Another is fermentation method. Through this we convert the biofuels like methanol, ethanol, bioethanol, like that. And another conversion is that this is related to the gaseous form. And nowadays this process is very much popular to generate the hydrogen. So that base is thermochemical conversion system. So my topic is on the gasifications. We are not going to the hydrothermal liquefacions or the pyrolysis. So here we can receive what from the gasification is called producer gases, and if it has been filtered out, some impurities are there that has to be taken out, then this is called syngas. So this is the basic route of the biomass to energy process. So first of all, the big solid waste has to be converted and is to be chopped in a such a way so that its surface area could be increased and it could be easily converted to the gaseous form within a particular time. So chopping is there, hydrating is there, drying systems are there, briquettes are there, purifications are there. Similarly, for the pulverized system, crushing of this particular feed, then biomass through the straw manure, fibers, sewage slush, many other organs are there. That is in the pulverized form. And this has to be transfer or feed it through the different gasification system, that is called either it is fixed gasification systems or this is fluidized bed gasification system. Fixed gasification system, there is three types: downdraft, updraft and the cross. And fluidized, basically this size is very less. Nearby 5 mm of this size has to be converted from the big biomass. And the producer gases which is converted from the biomass is the sum of carbon dioxide, carbon monoxide, water vapor, hydrogens, some amount of methane, char, tar and particles. So after these reforming methods, and this can be converted to the syngas, and through the water gas shift reactions and the Fischer-Tropsch technologies, we can convert this CO and H2 into the liquid form. And this Fischer-Tropsch technology is just like our earth, where between the rock there is so much pressure is there, and that pressure is used to convert the very old biomass into the liquid form. The same conditions we apply manually, so that this carbon monoxide and hydrogens can be converted into the different form of other liquid. You can convert it to the gasoline, you can convert it to the aviated gasolines, you can convert it to the diesels also, and you can convert it to the ethanol, methanol, and whatever types of the combinations of the fuel, that you can convert it through the Fischer-Tropsch technology, although this is very costly. So feasible use also there. So this is the little animations of the gasifications, where from the biomass which we used to collect, we used to put over the gasifier, different filters, mediums are there, and through that we used to collect the producer gases. But it is not easy. I'll tell you further the how we used to do it, so how, what is the chemicals and mechanism behind it. So biomass, each type of the biomass we cannot use it. There is certain qualities required. So those which have the cellulose and hemicellulose contents in the biomass is there, that will be beneficial for the gasifications. So these are the different temperature are there. In particular temperatures you have to achieve, then only gasifications could be happen, or it will produce the producer gas, otherwise it will burn completely. And there must be certain agents like a oxygens or the CO2 or the steam, like that. And this should be the limited conditions. So the basic problems of the gasification is that one thing is that one part we can say heat is also required, and partial combustion is also required, where oxygens used to be a limited portion. So this achievement is one of the very challenging for the different types of the biomass. And here some feedstocks are there, where corn straw, Delbourgin Sico, hazelnut shell, corn stalk, like this many particulars are there in the biomass. And if you go for the ultimate analysis, then this will be the bifurcations of the carbon, hydrogen, nitrogen, oxygen, and the sulfur. And here one thing is that those materials, so those feedstock which have the higher carbon and higher hydrogens, that will be the beneficial for the gasifications. And this will be achieved when we'll go for the proximate analysis, where the volatile matter of the particular biomass is higher. For the example, the leaf, simple leaf which is coming out from the tree, volatile matter is very less. So we cannot use this one in the gasifications. But with the blendings with the other, it can be utilized. So this is the basic mechanism of the gasifications, where the heat is being taken as a input, and different other gases is coming when the pyrolysis has been taken place, and finally the CO, CO2, H2O, H2 and CH4, such type of the chemicals as a fuel comes out from the gasification. And this is the basic chemical structures and the different heat zone in the gasification system. First of one, when you come from the above, when the material is going to be fit from the upper side, then total gasification system comes under the different zone, that is drying zone, then pyrolysis zone, then oxidation zone, then the reduction zone. So reduction zones, basically it converts the pyrolyzed fuels into the different form of gaseous. So these are the different reactions are there. I'm not going to details upon it. And combustions with oxygen, combustion with carbon dioxide for the steam reforming, then hydrogens, then water gas shift reactions, and methanation reactions. So all these reactions used to happen inside the gasification. These are the different gasifiers: updraft gasifier, downdraft gasifier, circulating types or entrain type gasification systems as per the requirement and as per the different efficiencies concerned. The compositions, what are the different compositions comes out corresponding to the different types of the gasifier. Gas quality, basically when we are going to use in the engine, then the tar should be very less. Tar content should be very less. In megajoule per meter cubes, these are the different qualities of the tars are there. The downdraft 15 to 300, and for the updrafts this is very high. So in case of the IC engine applications, we need tar. Otherwise, when you directly input inside the internal combustion engine, then this will choke the all suction part. Then in the second times or the second slots of the engines, you cannot run it, because it adheres all the linked part inside the combustion chamber, and it will be very difficult, and that called choked condition. So the standard is that it should less than 50 mg per meter cubes. Tar should be very less. But the remaining parts like updraft and bubbling, this can be used for the heating purpose. And so for calorific values is been concerned, downdraft calorific value is maximum 6 megajoule per meter cubes. Updraft is also nearby less, and bubbling is less, but heating capability as per the tar concerns is there when you tar is been injected, and this heat could be enhanced. How we can convert and how we can integrate the internal combustion engines to the gasification systems? So we have in the IIT VHU 14 kilowatt of gasifier units are there, and we have experimented on it and found certain result. So these are the different byproducts are there. So when you see from the top, so you can see over here that raw biomass, and here we have used 20 to 50 mm of the size. Then after this, some unburned may be there, char is there, and ash is there. In this gasifications, all the elements or all the products are used. Very beautiful. First of all, gases we can use in the internal combustion. Charcoal. This is very much beneficial for the heating purpose. And this is basically smokeless coal or smokeless wood. Another is there, that is ash particle. So this ash can be replaced nearby 10% of the cement. So this what we have achieved. So this is what we have obtained during the experiment with the gasifier and engine coupling systems, and maximum 50 to 60% of diesel we have saved from gasifications to internal combustion engine. And here this is ER is related to the equivalence ratio. How much air we will supply inside the gasification so that maximum gases could be come off, and accordingly if the flammable will be high, then it could replace the diesel. Another we have experimented on the coconut shell. As usual, we used to remove it. There is no use of it. But inside the gasification system, then after the gasification systems, you can find like this, and you can reuse for the heating purpose. only the gaseous has been removed. So that's why this coconut, the burned coconuts or the after gasified coconut, this is a smokeless solid fuel. So these are the certain results are there in terms of the brake power and emission level. And we found the NOx emission is also very less. And this is very much important for us to save our environment. And here we can see for the different compression ratio in engines, we have experimented and we found that in 18 compression ratio, we have reached nearby 49.05 diesel saving. For 50% we have saved the diesel. And these are the different heat balance charts, and we have found that what is the optimum conditions of the equivalence ratio in terms of the gasifications and similar to the emissions from an engine and corresponding to the maximizing of the powers, we have received some optimized point. So that is in the red color, that is 0.12 equivalence ratio and nearby 17 compression ratio, and load is maximized. Those similar results are there in terms of the brake power and indicated powers and the NOx emissions. The similar results we have received also, and this is very beneficial in terms of the fuel consumptions. So this is new designs what we are doing.
ये ब्लू फ्लेम ऊपर ही फ्लेम पे
So this like a further
अभी ब्लोअर भी चालू नहीं किया है ना इसमें, सिर्फ पानी का प्रेशर से.
we are going to develop
ब्लोअर चालू करने से भी कोई
burning device
यहाँ नहीं जलेगा.
where we can use it also. So this is basically inspired. This is flame, and what we have developed, this height would be a little bit 15 feet. 15 feet of height is there, and we can develop 20 kilowatt. This is designed for the 20 kilowatt of electricity generation. Some challenges we have: high cetane numbers and better lubrications and biofuels and the gases if we use in the engine. So these are the different strengths and weakness and opportunities are there, but threat is also there because of the Coal India and other things. They are not very much, they don't want to propagate the things because they have their own monopoly. Thank you so much for the attention. Okay, so question please, if you have any. Yes, sir, please. No, this is directly coming from. This is during the testing, sir. Yeah. And the story part I have not shown. Yeah. Yeah, please. Okay. The yield is yield in terms of the gases basically this is. So, okay, because gases what we are drawing from the gasifier, this gasifier we have designed, so 170 kg if you put it, and total 10 hours you can draw the gases from it. Okay, so that is the yield basically. So in terms of the meter cube per kg, this comes nearby 30. So this is what we have achieved. So we are also making this one mobile systems. Basically, in the marriage functions and other functions, people they used to take the big generator. Okay, so you just take this whole systems, one a big trolley, then you put the diesels and you put some for the starting purpose diesels will be used, and remaining you can use the coal or you can put the biomass, and from there you can at least 6 or the 7 hour you can produce the electricity, and that will be very less in comparison, cost will be very less in comparison to the diesel fuels. In that directions we are moving. Yes please. ये चल नहीं रहा है, how it will run, ये चल क्यों नहीं रहा है? Okay. Yes. ये blue flame. Yes, yes. Yes. Basically, in the gasification system, there is no waste. First of all, from the biomass, we are taking out gases.
अभी ब्लोअर भी चालू नहीं किया है ना इसमें,
Second
सिर्फ
one,
पानी का प्रेशर से।
after the gasification, whatever the biomass is, that is charcoal.
ब्लोअर चालू करने से भी कुछ
That is
यहाँ नहीं जलेगा।
coming out from that you can use for we have this can be replaced by the trust of this as well as so this thing can be. So there is no waste. So this is green technologies. Any more question, please? I'll be happy to answer. Yes, yes, very good questions. Yes. Basically, the plastic like this, you can crush it, but its temperature is nearby 700 degrees Celsius inside of it. For this, it needs 1100 degrees Celsius, and it should be very slow movement. One thing is that when you heat this one, then what happened? All the plastic used to agglomerate one place. ये बड़ा वाला अंडा बन जाता है. Then it will be very difficult to remove from this. So its technology is different. So that's why what we people are doing, we are mixing it with the biomass or the coal, so that this will not directly contact each other, and it will be separated and it can be heated from the coal and the other way, so that slowly it can be degraded. And certainly we can consume all the plastic waste and like that into the gaseous form. We are doing it. Yes, please.
Can we identify the gases like combustion reaction, or what type of gases, new gases after burning?
From here?
Yeah.
Basically, this is combinations of carbon monoxide, then carbon dioxide, then this is hydrogen, then methane. These all things are there, but main is that carbon monoxides and hydrogen, because it has the calorific value. CO2 has no calorific values. Methane we are getting the methane as well as the carbon monoxide and hydrogens. So these are main. We are separating the CO2, okay, by the sequestration technology, so that we will get the pure one. After that, what we are planning, so that this CH4 could be converted to the CO and H2, and this could be converted further for the methanol, for the Fischer-Tropsch technologies. This could be. So that's why nowadays different coal industries as well as biomass or some other industries, they are promoting to hydrogen production to the gasification. So this is a one way from the waste we can convert to the energy to the level of hydrogen. because nowadays in the Delhi, and other places, many hydrogen vehicles are moving. So they need hydrogen. Hydrogen cells is also there. From where we'll get the hydrogen? Because electrolysis process is very costly. 1 meter cube of hydrogen collections, it needs the equipment, what it call nearby 10 lakhs, very small. It's very costly. So the people are moving toward this by the filtrations or by the catalytic system, so that from the waste to energy to hydrogens we can convert. Yes, please. Yeah, definitely. We are working on it. We are working on it. Yes, we can definitely we can store it and we can utilize it. One challenge is there because H2 is there, so it reduces the calorific values later on. So that has to be again. Yeah. I mean, directly you can do. Directly you can take all the systems. You can take there, or you can compress the thing, compress the biogas or this producer gases in a particular tank, and thereafter you can. That way also we can. Alright, sir, please. Yeah, we have done it. This results good, very results is good, but the hydrogen contents is less. No, in that way, I don't know what the cow have eaten and what types of the dunk is coming out. So pure and non-pure, I cannot compare on it. Because one beautiful thing is that any type of the waste, if it is the leaf type is there, that you can crush it and you can make a briquette. Then you can put it. So this is one of the best method of waste to energy conversion. Yes. Okay, thank you so much for all your inquiry and your suggestions.
We extend our heartfelt thanks to our keynote speaker for delivering such an inspiring and thought-provoking presentation. Your insights and expertise has greatly enriched our understanding.
We would also like to express our sincere gratitude to the session chair, Dr. Gopalji, Graphic University, Dehradun, for his exceptional efforts in conducting today's session. Your contributions have been invaluable to the success of this event. Now, I would request our session chair, Dr. Gopalji, to felicitate our keynote speaker, Dr. J.V. Tirki, IIT BHU.
Now I would request our coordinator, Dr. Pushpendra Rathore, to felicitate our session chair, Dr. Gopalji. I would now like to introduce the session chairs for our next keynote talk session. Dr. Ravi Kumar Sharma from Manipal University, Jaipur.
Now I would like to request our session chair and our coordinator Dr. Pushpendra Rathod to present the Tulsi sapling to Professor Dr. Atul Dhar from IIT Mandi as a token of gratitude.
Okay, so moving ahead, we have next session. We have our keynote talk, a keynote speaker here. Let me introduce. So it's my privilege to introduce Dr. Atul Dhar. He is from IIT Mandi, Department School of Mechanical and Materials Engineering. Dr. Atul have a vast experience in the field of energy related materials. He currently is as associate professor and chairperson of the School of Mechanical and Materials Engineering at IIT Mandi. He have done his doctorate from IIT Kanpur, have postdoctoral experience from France, and have a very good experience in the field of regarding energy generation from fuels and alternate fuels. Thank you, Dr. Atul, for sparing some time from a busy schedule and coming here. And of course, you are coming from a very beautiful place, IIT Mandi, and the temperature here in Delhi, well, from tomorrow it's rainfall, but before that it was too hot. So you have to bear with that. Also, I would like to welcome the session chair for this session. He is Dr. Ravi Kumar Sharma from Manipal University, Jaipur, currently working as a professor there and heading the Department of Mechanical Engineering. He have done his doctoral from University of Malaya, had a vast experience in the field of materials related to energy, specifically thermal energy storage. One more thing that he is also my research collaborator, my field area, research area, and his research area is same. So we are working together, trying to do some good work in the field of thermal energy storage. So thank you, sir. Thank you, Ravi, sir, for sparing time from your busy schedule, heading the department there and coming here. Thank you so much. So without wasting any time, I would like to invite our keynote speaker, Dr. Atul, to deliver his keynote.
So thank you, Dr. Pushpen, for this kind introduction. And I would also like to thank organizers of this game, especially Dr. Basansi Karwar. So by taking advantage of background created by my previous speaker, so and I will try to reduce time because I'm standing between your lunch. So here the concept targeted to be presented is hydrogen supplementation in compression ignition engine. Suppose there is scenario that we don't have 100% availability of the hydrogen. So then what additional advantages can be derived by substitution of a small amount of hydrogen energy share in diesel engines. So that is the concept. And in previous talk, you might have noticed that concepts like syngas, where we have say 5 to 10 to 20% generation of the hydrogen along with some other carbon containing fuel. So in that scenario, what advantages we can draw. So we know that specifically for India, for transport fuels, more than 95% fuel is coming from imported source. And while we talk about transport fuels, it is mostly say diesel or petrol. And in some cases, for petrol substitution, there has been say in best case scenario about 10% substitution by ethanol. But mainly like we are having huge insecurity due to huge dependency on imported fuels. And top of that, we are having about say 80% transport fuel coming from this diesel route, and they are also considered to be quite dirty in terms of environmental pollution. So in that scenario, here I am going to present some strategy when some small amount of the hydrogen production can reduce some emissions. And then in the later part of the talk, there is say some prototype level effort to generate this small amount of hydrogen through some waste heat recovery through onboard generation on engine itself. So that is the planned outline. So we know that we have this picture in our mind that generally IC engines, they are major polluters, but I have put question marks with the implementation of these Euro 6 emission norms. Many times even the engine exhaust coming, it may be cleaner compared to the environmental, say, air quality. But anyway, if we are burning any carbon containing fuel with all the effort to clean the regulated pollutants, we are certainly adding some amount of CO2, and the stringent limit what Dr. Tirki pointed out in his previous presentation. So like there is this target up to 2100 gigawatt emission, but we have already contributed up to 1900. So we have very small buffer. So anyway, we have to shift to non carbon containing fuels, and same time there must be effort to reduce even the regulated pollutants. And unfortunately, like we are bearing the consequence of using polluting air sources. So like 22 of the 30 most polluted cities, unfortunately, they are in our country. So we have to make effort to shift to the clean energy sources, and especially the convenience we are deriving for mobility sources. So we have to face the consequences, because for say automobiles, these pollutants, they are coming in the contact of the big population. But for other sources like power plants, we may have this luxury that we can emit in the sparsely populated area and we can discharge in upper portion of the atmosphere. But for the automobiles, it has to be ultra clean. So then name of the some possible alternates is mentioned. So biodiesel, that didn't picked up in our country due to supply side choking. But for say electricity, we are having penetration of the electric vehicles in small power segments, but there is almost no contribution of electric vehicle in say part of the vehicles which are consuming most of the fuel. Ethanol has shown say satisfactory success story in the years where we have significant production of the sugar cane. We have achieved up to 10% of the substitution in some states of our country. So CNG, we should not say like it is alternate fuel. It has nowadays found its place as a main fuel. And hydrogen, like of course there are many demonstration projects, but there is questions about how we can have long-term supply and storage issues. And then there are some future fuels like methanol, DME, and NS3 that we are targeting as a strategic mix for powering our transport. So while selecting a suitability of any fuel for transport, we have to focus much on the specific energy storage density. So that diagram is just comparing how like alternate sources like compressed hydrogen or metal hydride based hydrogen and electricity, they perform with respect to our current benchmark of diesel and petrol. So then it appears that this metal hydride based hydrogen storage and this hydrogen storage at 700 bar, so they are say almost comparable to the this lithium ion based batteries. So this the volume and the weight what power sources like hydrogen and large scale electric vehicles in terms of battery storage they are going to occupy, they are having same level of energy storage density. So that is the major reason that in the data of the penetration of EV in the commercial and bigger vehicle, it is almost zero. But of course, we see some positivity for electric vehicle based alternate transport in terms of smaller vehicles. And if we have to strategically plan the alternate transport scenario, so then there are some studies which show that hybrid vehicles, they are going to be greenest strategy compared to the 100% electricity. But anyway, in the interest of time, I will not discuss that in much detail. So then coming to original issue. So there is also equal promise for hydrogen based say powering of the transport sector, but supply situation is not very promising for hydrogen. So then as an intermittent transition strategy, as a bridging strategy, so then H2 diesel dual fuel engines, what advantages we can derive that I am going to discuss. So then these data, they are showing if any engine is being operated with say up to 30% hydrogen energy substitution and rest of the energy is coming from diesel. So then what is the effect on in cylinder pressure as a say causal parameter, and then what is the effect on emissions and performance, that I will quickly show. So then it shows that if any engine which is designed for say diesel, and if we substitute say up to say 30% of the hydrogen, and for NOx mitigation there is a 10% of the exhaust gas also supplied along with the intake air. So then there is some bigger fluctuations observed in the peak pressure compared to the diesel only application. So because we know that auto ignition temperature of hydrogen is quite high compared to the diesel. So that's why those initial ignition challenges, they are reflected in terms of higher variability in cycle to cycle peak pressure. But if we compare in terms of say magnitude, say then we can say that up to 30% substitution, that doesn't have any significant adverse effect on peak pressure. So what is the effect of this small fluctuation in the cylinder pressure? So one thing, we are sensitive for any powertrain, what is the vibration experienced on the engine, that is ultimately transmitted to the user in terms of less or more vibrations felt while you are riding that vehicle. So then it makes sense to also quantify what is the effect of the change of the fuel on the vibrations produced on the powertrain. So how that is measured? So then we can measure the vibration on a particular engine in motoring condition where no combustion is happening, and then how particular vibration peak happens when combustion is happening. So then contrast of these two images, what additional factor is coming when combustion is happening, that is indicative of combustion induced vibration. So here it is qualitatively showing that combustion is adding to significant vibration. So by this differential method, so effect of hydrogen's substitution in diesel engine that was measured. So then it also shows that there is say a small amount of vibration increment once we are putting say 30% hydrogen at 100% load compared to the diesel only operation. So then in terms of variation or fluctuations in the peak pressure and associated vibration increase, at least these two challenges we have identified. That's why it appears that we need to identify what is the say maximum portion of the hydrogen substitution that can produce tolerable effect. So based on this say peak pressure coefficient of variation, so this 20% or 30% substitution that appeared acceptable. So then next part was to see what is the effect of this hydrogen substitution on major pollutants. So if we have to interpret like these studies, so in best case scenario, suppose we have substituted 30% diesel with 30% hydrogen, so then more than 30% reduction in pollutants, that is going to show that there is a synergistic effect along with the just material substitution of fossil fuel with pure hydrogen. So better to interpret what is the cumulative effect on various pollutants. So in well optimized strategy, so there was about 35% reduction in the NOx with synergy of the hydrogen as well as substitution of some amount of the exhaust gas. But because this diesel engine was designed for diesel only operation, so this 30% hydrogen substitution resulted only 21% reduction in the CO2. So then it shows that there is further scope for optimizing this engine to handle diesel and hydrogen mixture. In the case of CO reduction, it was almost 30%, actual value indicating here 27. For particulate matter, about 20% reduction was achieved and 26% for total hydrocarbon. And for aromatic hydrocarbon, though this is non-regulated pollutants, but even non-regulated emissions should be monitored while we are changing any fuel. So in this case, there was increase in aromatic hydrocarbons while we were attempting co-combustion of the diesel and hydrogen. So then while seeing some pollution related advantages by this co-substitution, so then next thing is, as we know that there are significant challenges in the generation of the hydrogen. So then what is the possibility of onboard generation of a small amount of hydrogen through exhaust gas recovery on the vehicle itself? So from that perspective, I will quickly show what are the few options through which some exhaust heat recovery can be done and what are the strategies required for converting that recovered heat at least to certain fraction into hydrogen. So then generally for automobile application, so these three routes, they are most prominent, named as turbo generator. So here it means some extra turbocharger apart from which one is compressing the intake air needs to be put. Then second route is the thermoelectric generator. So on the exhaust line, so specific materials which when subjected to thermal gradient, they produce electricity. If they are put on the exhaust line and outer surface, if it is properly cooled, then we can generate some small amount of electricity. And third route suited for say bigger vehicles like trucks and locomotive applications. So there we can afford to install even more complex system named organic Rankine cycle based system. And among these three systems, like system complexity keeps on increasing while we move from this turbo generator to organic Rankine cycle, but in same proportion their typical efficiencies also keeps on increasing. So typical value, like for turbo generator, we can expect up to 2% efficiency in waste heat recovery. For thermoelectric generator, it can be 3, and well optimized organic Rankine cycle 5 to 6%. So quickly, so this shows like one prototype attempt to install extra turbocharger, and this arrangement is simply showing what is the regulatory mechanism to share the fraction of the exhaust in one turbocharger, which is compressing the intake air, and only the surplus should be diverted to this waste heat recovery mechanism. So that's why we need to install some properly controlled valves so that there is no disruption experienced by the turbocharger, which is integrated with the engine, regulating the intake air supply. So then, yeah, so this diagram shows the installation location of this second turbocharger, which is meant for this waste heat recovery, and then mechanical energy of this turbocharger was converted into electrical energy by this BLDC generator. So this shows like in this say retrofitting with the variation of the speed of the turbine, what was the RPM of this turbocharger and what amount of the voltage was generated. But the continuous operation of this retrofitting was not possible because there were problems in the lubrication of this retrofitted turbocharger. So reliable integration was not successful. So then quickly I will also mention about this prototyping effort of this thermoelectric generator based implementation. So then it shows that, yeah. So some muffler like heat exchanger arrangement needs to be installed in the exhaust line, and then these thermoelectric generators needs to be provided heat absorbing surfaces, and as I was mentioning, the temperature gradient is the source of electricity production in this thermoelectric generator. So then other surface needs to be cooled. So for reliable cooling, we need to either flow some liquid, or we can have some PCM based temperature control. So then it is showing the component, say actual installation of that component in this right side diagram, and here it is showing that because there are say multiple small units of thermoelectric generator, so then for any meaningful power collection, so some electrical circuit needs to be designed to feed the power from multiple small generators. So then in this case, because the system is simpler, so it was deployed for longer duration, and even the power output was measured by drawing the current. So this prototype was able to generate up to 50 watt, and this shows that if like this system can be scaled up, so it can generate significant amount of hydrogen. So then next thing was because the initial part of this study was to generate advantage in emissions by generating some small amount of onboard hydrogen. So this electricity produced from this thermoelectric generator that was converted into hydrogen by in-house fabrication of electrolyzers for HHO production. And like in electrolyzer operation, separation of this hydrogen and oxygen, that is a big challenge, and specific membranes needs to be designed. But fortunately, in this particular operation, even if we are feeding say pure oxygen along with the hydrogen, that is expected to help in the combustion. So that requirement of segregating hydrogen and oxygen was not compulsory. So with that flexibility, these electrolyzers were constructed by using nickel and stainless steel as the say anode and cathode respectively. So then for design of this electrolyzer, the surface contact area between the water which is being split and the electrodes, that is one of the significant parameter. So then it shows if we are making these corrugation patterns on the electrodes, so then how this current produced by supplying same amount of the power changes. So based on that, so this triangle plus square shape that produced maximum current, that is a reflection of say better utilization of the electrolyzer surface area for meaningful hydrogen conversion. So then just to have some idea, so then actual system attempting to have about 150 ml of the hydrogen production per minute. So that was also having multiple units of these electrolyzers that was constructed and placed alongside with this engine. So then quickly I would like to show. So this 700 ml per minute, a small amount of the hydrogen was produced, and it was co-combusted with the diesel itself by using same strategy what I was describing in the beginning. So that has significant effects for reducing total particulate concentration. So like it shows particulate combustion was reduced while in compared to diesel only combustion. And there was say almost same amount of the NO production, and this HHO fumigation that was also helpful in total hydrocarbon emission reduction. Okay, so then in the summary, I will just say that I discussed about the what is the possible advantages by small amount of the hydrogen combustion along with the diesel, and some pathway for this this onboard production of the hydrogen. So
whenever we are running bike and we need, the bike should give 80%, 90% average. So, and bikes are generally petrol engines. So my concern is if we are adding then what will be the effect, and then it will be benefited to the most of the Indians, not only the businessmen for trucks and the heavy duties.
In the scenario of the petrol engines, so if there is any amount of say hydrogen available, but so that is certainly going to happen in both say pollutant, further reduction of the pollutants, as well as some improvement in the pollutant. But of course, like at the level of the motorbikes, there will be some additional system complexity. So I hope you might have heard that recently some automobile manufacturers they have done the CNG one. For CNG, its storage is less challenging, but having this hydrogen storage on the bikes, there is doubt that like users will accept that there is excess storage space in the hydrogen cylinder. But if say there is something like this onboard generation concept, and even this like the prototype systems what I was showing, they were quite bulky. No, say bike user is going to accept in this current. If they become say compact, so it takes 5 years, they may be possible, but
I think a carburetor is used in petrol engine. So where the fuel are going to mix, and in diesel engine, I think only injector is used. So the mixture can be possible more easier.
hydrogen will go similar to this carburetor. Along with the air, hydrogen will also go.
Also, so it is more easier in petrol. I think it is more easier.
For petrol, it is very natural.
Okay, thank you, sir. Thank you.
Any more questions?
We have CNG and LPG. They are in in cars we have cylinders. And LPG have one of the biggest issue of, there are several cases we have heard that it got fire. Okay, so is there anything that storage for hydrogen, safe storage that you are looking?
One thing, yeah. So, of course, that is one of the most hot or biggest research area in the transport, alternate transport domain. But I am not having seen sufficient expertise to comment on the state of art of the this hydrogen storage. But now, like in terms of plant regulations and the hydrogen policy of the India, so we have these two routes, 700 bar composite hydrogen cylinders, and second one these metal hydride based hydrogen storage. So there, this challenge is if
we have guidelines for this. Government of India have guidelines.
And then this global standard is if like 8% by mass, if we can have any storage system.
Okay.
So then people have correlated it with respect to the driving range requirement of the vehicle, etc.
Dr. Atul, this is very good, and many things I have learned from your slides. Little bit doubts there. How you are maintaining the equivalence ratio, whether this engine is working on lean mixtures. So
Working on?
lean mixture.
Yeah.
So how you are maintaining this lean mixtures? At what lean mixtures it is working?
Yeah. So while conducting these experiments, equivalence ratio was not controlled. So only relative energy share of the two fuels that was controlled. So for doing that, like while conducting this diesel only operation, amount of the diesel required that was the measured, and then equivalent same amount of the diesel that was reduced, and same amount that excess this reduced energy requirement that was supplied through hydrogen. And then if there was any say shortfall from the targeted load, so then some additional amount of the hydrogen was supplied, or it was just tuned in that steady state condition.
Okay,
But there was no active effort to control the equivalence ratio of the burning mixture.
Okay, basically you are transferring the hydrogens in the suctions of air portions.
Yeah.
Okay, because if you are transferring the hydrogens to the air, then the amount of air will be reduced.
Yeah. So in here I didn't show, but there is significant. Suppose if there is a 30% energy share coming from hydrogen, so then roughly there is 20% reduction in the volumetric efficiency due to this substitution of air by hydrogen. So that's why, like in diesel only combustion and diesel plus hydrogen combustion, this equivalence ratio they were not same.
Okay. So that's why you have taken the two turbocharger.
No. Purpose of second turbocharger was just to demonstrate this strategy of waste heat recovery. So that second turbocharger was being attempted to fix some generator so that some electricity can be generated, so that onboard HHO can be produced.
Okay.
So
in the first turbocharger is there where air we are supplying in the higher pressure. Then and again we are supplying the hydrogens along with this. Then I think it will be better if the higher pressures of the oxygens will be supplied or the air will supply. Then I think the proper equivalence ratio could be maintained as it was in the diesel.
So in say further investigation of this study, of course it is interesting to see I was telling that if I am substituting 30% hydrogen, so then more than 30% reduction or 30 should be there. But in most of the pollutants, it was between 20 and 30. So there is significantly there is a scope for optimization of the combustion parameter, and there this
Very good.
equivalence ratio, of course, that needs to be monitored.
I got it, sir. Thank you so much, sir. Thank you.
Final question from sir. What will be the levelized cost of hydrogen production and use it in IC engines?
So
approximately.
So like here, whatsoever experience I have, it is from the waste heat recovery from onboard generation. So then here, like it is safe to say there will be no operational cost because it is coming from waste heat recovery, but of course there will be system cost. And then if we are trying to answer it in terms of suppose we are bringing hydrogen from some other production means, so then it depends on from what route we are producing. So nowadays, like most of the hydrogen what we use, it is coming from the this reforming of the methane. So then of course in energy terms it is much costlier than using the methane, but there is effort for greening this hydrogen by electrolysis or thermolysis through this solar route, but those systems are not mature. Nowadays whatsoever reference we have, it is through the steam reforming, and then you should say it is at least 1.5 to 2 times of the cost of the CNG. Okay.
Thank you, Dr. Atul. Thanks for a wonderful presentation.
Thank you, sir, for a nice, wonderful presentation. Now, I would like to invite our session chair to facilitate the keynote speaker with the memento of Flame 2024. So, please give a big round of applause.
Now I would request Dr. Pushpender Rathore to facilitate our session chair, Dr. Ravi Kumar.
Can we have a round of applause, please? Now we would be moving on to our third session of the day. We have Professor Dr. Sachin Singh Gautam, IIT Guwahati. So I would like Professor Pushpendra Rathore to present the Tulsi sapling to Professor Dr. Sachin Singh Rathore. Sorry, Gautam.
So, let's quickly move on to our last session, session third. It's my honor to introduce Dr. Sachin Singh Gautam. He is currently associated with IIT Guwahati as an associate professor in Department of Mechanical Engineering. Specifically isogeometric analysis, contact problems, and GPU computing. Recently, he has also started to explore a new area of machine learning application in finite elements, especially contact problems. Published papers, patents, app books, and a very vast experience of organizing various technical conferences at IIT Guwahati. So thank you, Sachin sir, for sparing time from a busy schedule. Now I would like, also I'll request, since our session chair is not there, so I request Dr. Ravi to kindly be a session chair for this session. So now I invite Sachin sir to please give a keynote talk.
Yeah, thank you very much for this nice introduction, and thanks for inviting me for this talk. So I realized that, profoundly realized that I am between lunch and you guys. So I'll make it quick, although it's a very vast topic out there. But I'll just give an overview. So it's isogeometric contact analysis. Basically, initially I thought I'll have 1 hour session, so I included when I was giving the abstract review, result, future trends. But in this, I'll basically concentrate on the results part. And all these work are basically not mine, it's my students' work. So Sumit is the current PhD student who works on this 3D contact problems. And then Vishal was the earlier who started all this work. He's now in KTH, Sweden. Akshay did a part of the pre-processor work. He is doing PhD in TU Munich. And Adarsh has done the machine learning part. So on behalf of all these students, I'm presenting this work. So these work was sponsored by SCRB and ISRO jointly through Imprint project, where we develop this isogeometric contact module for their finite element software Feast. So which is one of the kind finite element software, which is totally made in India, was started by APJ Abdul Kalam back in 1980s. Now it's a very well-established software, very cheap, and so in coming future, we'll see isogeometric contact implemented inside that software. So starting, we have few topics, some introduction to isogeometric analysis, contact formulation. This is our discretization scheme that we proposed recently, some results, some application of machine learning in IGA contact, and we'll then conclude. So this is our lab, primarily focuses on large scale contact and small scale gecko simulation adhesive contact. So that's a nano scale, and we've been funded a lot by SCRB, VSSC. Recently, we have a project from ARDB for machine learning applications. We have collaboration with Cummins and Professor Sauer from RWTH. Now he's in another university. So these contact problems occur a lot in nature. So you have car crash simulations to do, tire simulations. You have soil foundation interaction simulations. At small scale, you have gecko contact. So you will know all these lizards walking on the wall. They use this adhesive contact, multi-scale adhesive contact to walk on the wall. With this, you can design robots. People have designed robotics out of that. And you have biomechanical applications. So a lot of these applications are there. Other than that, you have sheet metal, gear, all these kind of simulations occur where you need precise simulation of the contact. Okay. So this is the ancient history. I mean, Egyptian used their understanding of contact problem to make pyramids. And then Leonardo da Vinci had certain understanding. Euler had a certain understanding of friction. Okay, so these were the earlier works. So that's what called ancient history. And in the modern history, I started with Hertz contact problem, 1882, well known. And then in 1956, Turner came up with finite element method, and that led to the start of simulation-based work in contact problem. So that started with Wilson and Parson, and then a lot of these people work. So these are all in contact problem. A lot of these novel contact simulation which you find in finite element software were developed in the last century. Now what happened is recently, I mean, I'll go, yeah. So contact problem, this is the classification. You can classify contact problem into mechanical contact, direct or self contact. You can classify them into the nature of contact, rigid, deformable contact. and frictional behavior based on that also. If you neglect friction, then you have frictionless contact, otherwise you have frictional contact. On the deformation behavior, if you have small deformation contact problem or a large deformation contact problem like in that automobile crash simulation. So each of these kind of contact problem presents a different kind of challenge. The algorithm become different. Okay, so you can have 1D, 2D, 3D contact. The 3D contact is the most challenging part. Okay, so isogeometric analysis, coming to it, I mean, it was proposed, the first paper came out in 2005, and since then there has been an exponential increase in the number of papers. This is only till 2021 that I'm showing, because that was the slide of my PhD student for the state of art. And you can see that right from first paper in 2021, there are 400, 500 papers coming totally in isogeometric analysis. Okay, that's the first work that came out from the group of Hughes. And the so what is IGA? IGA is a unification of CAD and finite element analysis. So people who have done finite element analysis will realize that you first model the geometry, take it into a finite element, any finite element measure like hypermesh, and then you import that into a finite element solver. So there is a certain idealization that is there in each and every step. So if you make a CAD geometry, then you approximate, and then you use your solver to like ANSYS or all to do the simulation. So that's your finite element analysis. And so in finite element analysis, for example, if you had to model a circle, and if you use linear elements, you'll get something like this, which doesn't look like a circle, although one can intuitively make out that this is a circle. In IGA, what happens when you do the CAD's modeling, the same basis function which are used for geometry, which are called splines, are used in the PDE solver. So this mesh generation, that part is basically sort of taken out. You have the exact geometry which is modeled, which is shown here. So in finite element simulation, you will have something like an approximate geometry, but in isogeometric analysis, you will deal with exact geometry. Okay, so this is a slide which is, data which is taken from Hughes. So in traditional finite element approximation, finite element analysis, approximately 80% of the time is taken till mesh generation. Solver only takes around 20% of the time. So 80% is a lot of time for companies to invest. So in that's where isogeometric analysis comes in. It tries to combine the CAD engineers with the finite element analysis, and so that this 80% of the time can get reduced. Obviously, there are some bottlenecks still existing, but you can have geometry. So the idea is you can have geometric error-free simulation, and basically the computational time for simulation can be reduced. Okay. So what are the advantages? You have accurate simulation, which are robust, efficient, and because of local refinement, you can have easily incorporate adaptivity. Okay. So what is the advantage of IGA is in one of the papers, you can see that traditional finite element simulation takes around 550 hours. So this is a simulation of erratic wall from the group of Hughes. What takes 550 hours to simulate can be done in 1 hour and 15 minutes during isogeometric analysis. That's a significant reduction in the computational time. And in terms of resources, you can see here, for example, in isogeometric analysis, what you achieve in like 50,000 approximately degree of freedom. Traditional finite element will take around 1 million degree of freedom. So that's a reduction in the computational effort. So that's a significant advantage you have in isogeometric analysis. So it's becoming very popular. A lot of industries using. LS Dyna, for example, has incorporated IGA and they're working into it. Companies like Mahindra and all this, they want to explore, but the problem is it requires a lot of expertise to work into. And what are the challenges in traditional contact analysis? You will have non-physical oscillation because you have approximate geometry, high stress concentration, which are not physical at the contact zone, and contact detection also is a big problem. Okay, so what is the solution? You can either do the smoothing of the contact surface. It's a well-established strategy in finite element analysis, or So you can have P refinement or a higher order refinement. So in IGA, there are various refinement strategies which can be used. And we have done some comparative study of various refinement strategies in one of our recent papers. And so I'm skipping all the review part. If you are interested, you can see our one of the recent paper in applied archives of computational methods of engineering, which totally deals on isogeometric contact review, contact problems. So I'll skip all this B-spline. Okay, so the idea of B-spline basically is that you have a knot vector. Okay, and then with this knot vector, you can generate what are called spline functions. Okay, recursively you can use Cox-de-Boer recursion formula to generate these functions, and then you can generate higher order function with repeating knots. Okay, so that's the idea. So the main features are here. You will still have the partition of unity property in B-spline function. So you can represent complex curves. So these red points are basically your control point. Black points are basically your knot vector locations. You can represent curves. You can have surfaces. You can have solids, which you can construct using B-splines. But one of the disadvantages, you cannot have conics, which you can use using construct using B-spline, for which you need to use nerve basis function. So using nerve basis function, you can represent conic sections. Okay, so and what the idea is, apart from your basis function, you also utilize weights. That's how you get this term non-uniform rational B-spline, because each control point has different weights, so which is not uniform. And these knobs are basically utilized in the isogeometric analysis. So here you can have curves, conic sections, which are not possible in traditional B-splines. So you can have 2D, 3D, all kinds of complex geometries that you can model for analysis. Okay. And then from the context of refinement, there are different refinement strategies analogous to finite element analysis. You can have knot insertion, which is like inserting new nodes in the finite element. Like in finite element, you insert new elements. So that is akin to like knot insertion in isogeometric analysis. You can elevate the order of the basis functions. So you can then you can do knot insertion to get what is called K refinement. So K refinement is not existing in finite element analysis. So this K refinement is what we use in our simulations for contact problems. Okay, so the idea, one of the key idea which separates isogeometric analysis and finite element analysis is, in finite element, the parameter space, psi eta zeta, the parameter space is local to every individual element. Okay, so each element will have its own parameter space. But in isogeometric analysis, the parameter space is local to an entire patch. So in isogeometric analysis, work in patches, patch of element. So like this is called a patch of element of two elements in one direction, one element in one direction and three in another direction. So this patch is what isogeometric analysis deals with, and FEM basically deals with one element at a time. So that's the key idea. Okay. So these are the flowchart of a classic finite element code. I'll just skip that. So coming to the formulation, so your mechanical boundary value problem that you have has to be augmented with contact constraints when you try to implement, and what you get is the contact boundary value problem. So you convert, as you do in nonlinear finite element method, you take that strong form, convert into a weak form, and then you do isogeometric discretization. You get a system of nonlinear equation which you solve iteratively using Newton-Raphson scheme or any iterative schemes. And how do you implement this constraint, which have to be both in the normal and tangential direction? You have different kind of formulations existing. You have to implement that at the contact point. So that also I'm skipping here because half an hour is not sufficient for that. So that's our idea that we published in 2020 in Computer Methods in Applied Mechanics and Engineering, which is called the VO nerve discretization. So contact is a surface phenomenon. So what you need is something which is not going on in the bulk but happens only at the surface. So if you want to refine, basically in isogeometric analysis, the unknowns are at the control point. Just like in finite element method, your unknowns are at the nodes. But in isogeometric analysis, you can have control point which are located outside the geometry. So if I go back and if I just show you this picture again, just to make it clear, you see here, so this is your geometry, but the control points lie outside the geometry. Okay, so in finite element method, the nodes will lie always on the geometry, but here the control points lie outside. Okay, so and the unknowns are at the control points in isogeometric analysis. So if you want to do refinement because of the tensor product nature of nerves, if you do refinement at one surface, that will be reflected all over the domain, and which is not required. We want refinement only at the surface, not at the bulk, because that's where contact happens. The more number of control points, more accurate your results would be. So that's where we came up with variable order nerves discretization strategy, where we could generate more number of control points only at the surface, not disturbing the number of control points in the bulk. Okay, so we had two different strategies. One was called the higher continuous nerves. I mean, you can refer to this paper, our recent paper, where we have given in detail all this. So I'm skipping here because I have to, time is less. And we have higher order discretization. There are two different strategies we had. And with these strategies, we found out eventually that we get much accurate results in much lesser time as compared to if you do uniform refinement, which consists of bulk also. Okay. So as a summary, this VO nerves, they are used only at the contact layer, and a large number of degree freedom can be introduced without affecting the mesh. Okay. And the number of all control points always also increases only by a slight amount. And I'll just skip that. Okay, so these VO nerves have the non-negative property that the value of the shape function never goes less than 1, which unlike in finite element can go less than 1 in certain part of the elements. We have the partition of unity property, which is essential to represent rigid body motions. Okay, and using this in the using the isoparametric concept and using nerves as a shape function, you can use the same strategy for approximating the displacement and inside an element. So this R is where your nerve base function rests, unlike in FEM where you have the Lagrange shape functions. Okay, so 3 dimension. I mean, I'll just skip all those. Yeah. So coming to the results, whenever you develop in simulation any new strategy, the first thing you have to do is validate your findings. So we started with validating the 2D Hertzian contact problem, which is very standard problem. Looks very easy. It's extremely tough to do. And in all those NAFEM's benchmark manuals and all, you'll find this first problem. So if you can really simulate, so this is the result that you want to simulate. And this is a 2D small deformation problem. And you can see with this coarse mesh and fine mesh, we can get the reference results very easily. Okay, so that validated. We then went to two-body deformable problem. This is a die slab contact problem. And this is the literature result, and this is what we got. And we again found out that our results are coming similar to what this reference results are there. So that's how the simulation goes. It's a large deformation problem. Then we move to 3D Hertz contact problem with the same problem, 2D, but now done in 3D. And again, we found out that this 3D isogeometric contact, the results from the reference, that is Hertz analytical results and our results match very well. Then we went to this validation of two-body large deformation problem. So that's how we simulate, and we found out the reference results and our results match very well. Okay, this is the result from one of the group working in isogeometric contact. So our results from VO nerves and reference results work very well, and we had certain advantages. Okay, now this is the another die slab contact problem. Now here we use VO. So validation problem we did not use VO. Okay, so here probably we started using VO nerves, and we showed that the normal and tangential tractions, which show a lot of oscillations because of the discretization schemes, can go down significantly. Like this pink curve can be much smoother when we use VO nerves. Okay, so this is 2D problem. This 2D ironing problem. I mean, you can clearly see which these oscillations can reduce significantly. Okay, so I'll skip all those. And also we had second order convergence. So whenever you have in simulation any strategy, how your results converge to exact solution is converge should be ideally quadratic, which means if you're not quadratic, there is some error in your formulation. So we had quadratic convergence in all our results. Okay, so I'll just skip all those. Okay, so this is Hertzian. Again, I'll skip. I'll just skip. Yeah, this was two body large deformation. This problem of two rings. That's how it goes by. And here also the results from the literature with 4 different meshes that we took. Here only 2 results are there. So this is conventional isogeometric results, and this is with VO nerves. And we found that our results were much better than for a similar degree of freedom as compared to the traditional nerves isogeometric nerves formulation. I'll just skip all this. We also tried on adhesive contact problem. This is a nanoscale contact problem. So we modeled this gecko's patella as a strip, and we peeled that off from a surface by applying angular moment. And here also, and this adhesion actually consider van der Waals adhesion. Okay, so we also found that with our conventional approach, the oscillation again went down. We got very good results. Okay, and results converged quadratically. And then we moved on to what are called the large deformation, really 3D large deformation problem, which are very challenging to solve. So these red dots are your control points, black are your not vector locations, and these are some of the material properties. So obviously this was frictionless results, and you can see the amount of deformation that the slab goes when the die is compressed and then dragged along. So the way it goes is first you compress and then you drag along, and the results that we get again we match with the reference results. It comes very nicely, and we had much smaller oscillations as compared to conventional results that people have. Okay, so now we did series of simulations. So this was with friction, die slab contact, which we called simplified setup. Okay, it's like a 2D problem only. In the third direction, we just extend, and you see that with adaptive VO, with very coarse mesh also, we had very smooth results. Okay, so I'll just skip all those. So then the block was now made really 3D, but the die was aligned with the block. Again, we had similar findings. Then what we did was we rotated the die. Okay, so block was like this and die was rotated, and we checked the convergence of our simulation. That whether the non-matching in the mesh causes any convergence problem. We did not find any problem. So everything was smooth. Okay, and then finally what we tried was the die slab indenter with friction. So the first case was there was compression and sliding. Okay, again smooth results. Then we had compression and rotated sliding. Okay, so you do the compression and then slide it along with rotation of the die. And again, for this is a very challenging problem in contact. We got a very smooth results. So this results is under review in International Journal of Numerical Methods in Engineering. I hope it get accepted. And finally, so this is application of machine learning. I'll just skip. So we wanted to see whether machine learning can help us in simulation of contact problems in isogeometric. So we did simulation of 2D Hertzian contact problem, and I'll just skip all this. This is the DNN architecture that we use, and this is the IGA result. This is the deep neural network results, and this is the error region. This gray zones, and we had very good match with the IGA results with DNN results. Obviously, the DNN result take only 1 second to simulate, while IGA will take around 15 minutes to simulate. So there is a significant advantage in using DNN. Okay, but there are some situation we get more error that we have to explore. Okay, so a large number of our results belong were in the mean absolute error or very less. Only few had very large mean absolute error. Obviously, with some kind of strategy, we can reduce that. I'll just skip all the. Another problem that we tried with machine learning was this 2D ironing problem, obviously with friction. Okay, and here also we developed this for various displacement in the X and Y direction, Young's modulus and coefficient of friction, various parameters we trained our network. And then what we did was we designed the architecture and we simulated the forces, horizontal forces with load step, what we got from IGA and what we got from the artificial neural network. And you can see that we can capture the large deformation behavior very well. Okay, this is a time dependent deformation. So we can get the results. Obviously, some places we are still getting a lot of errors, which we still have to explore. But still, this is only 6-month-old work that we did. Okay. Yeah, in some cases, some samples we had huge errors. We have to look into that. Okay. And again, yeah, this is 2D ironing problem. This is the vertical forces that we tried to simulate. Again, in vertical forces also, we had good matching with in most of the sample, but in some of the samples you'll get more error. So again, we have to look into whether where our training data set is not proper. So this basically happens when your training data set is not proper. But then when we look into, so these are the worst results which lie here, and these are the best results which lie here. So a large number of our simulation results lie in the very, this mean absolute error is very small. Okay. And this I'll just skip. Okay. So what is the future outlook? So the IGA contact is more accurate, robust and efficient. But you need to have a generalized pre-processor for isogeometric analysis, which still does not exist. So that is one of the bottlenecks of application of IGA in real life problem. You can have adaptive variable order nerves. That's what we are working on. Extension to self-contact. So that's what happens when you have a crash and the automobile components come in contact with each other. Extending to dynamic impact simulations. Now this machine learning application we have started, but it remains largely unexplored till now. Then we can go for large scale contact problem. In all the problem that we showed, the contact was only at the particular zone. But what happens if you have contact at hundreds and thousands of such zones? Then you need what is called high performance computing. That's one of the things that my student in TU Munich is working on. So high performance computing applied to contact problems. You can apply all those to biomedical field. That's an area which is unexplored. And the application of contact to small scale problems, which has applications in robotics, basically space. Okay. And multi-body contact problems in robotics. Okay. So that's where a lot of applications are there. People are not worked into. So with this, I'll acknowledge our funding partners, students, staff, and then I'll like to end the talk. Thank you very much. Okay.
Thank you very much, Dr. Gautam, for such wonderful presentations. Can I have some questions from the audience side? Anyone?
Thank you, sir, for your really nice presentations. My one in my thoughts, I can just came this very simple question for me. Sir, we are working with the IGA and FE and finite element analysis.
You're good.
And,
No, Acha.
Yes, sir. So how this much of a time period is reduced in IGA actually? Because if some work we are doing very fastly, and the result may have some errors higher compared to the
Time period means by time period you mean basically the amount of time required for a simulation.
Yes, sir.
So I showed one slide where in traditional finite element simulation or like aortic wall, I mean heart, I mean you have the very challenging fluid structure interaction going on. If you design a wall, that kind of simulation, what FE takes around 550 hours on a multi-core parallel machine, IGA can do in 1 hour 15 minutes. That's 100 or 2 order of time which is saved, right? And like in terms of the degree of freedom, what FEA requires, for example, 1 million degree of freedom, IGA can do in like 10,000, 50,000, something like this. So your this more degree of freedom means you require more memory, right? I mean, even though nowadays we have 128 GB workstation available, but then if you can reduce that, if I can, so with 50,000 I can go to 1 lakh and get very accurate result, which in FE may require days to get, right? But the only challenge with IGA, which nobody talks about, is the preprocessor part. How do you get the position of the control point, red dots?
That exactly.
Nobody tells you that. And that's a proprietary thing. Only Rhinoceros software, that 3D Rhinoceros software is there. That can give you in a certain format. And people are developing this preprocessor part. FE is well established. That hypermesh is there. You can just import a geometry and you can mesh. But in isogeometric problem, not only contact, isogeometric, the location of those points are not available. We have designed a preprocessor. We have published also results. But we already have that.
Although the points are not lying on the same line, but still we are getting good results.
Yes.
So
because that's how CAD geometries are made. So you interpolate based on the location of the control points, the shape function and the weights. Now it works like that.
So all we can move with IGA, I think. So we should leave that FEA part, I think.
No, FEA is well established. See, FEA came 70 years back, 1960. So many of the technologies are well established. The industries are well trained. You have Abacus, ANSYS, LS Dyna, COMSOL. They are all into finite element analysis. They will not just simply move into this area. Like LS Dyna, I know, because LS Dyna is developed. I mean, not exactly. ANSYS has got, my friend is the team leader. It's after LS Dyna. So he develops a lot of LS Dyna. So I know from him that they are implemented. A lot of challenges are there. There are not many people who work in that area. But Mahindra looks for that. Siemens, for example, my student works in Gurgaon. Okay. So Siemens internally is developing this IGA codes.
But my only concern is we are reducing time also, and we are getting not getting the point on the line also. But still we are getting good results. That's why.
Yeah, because that's the nature of the this nerves, no? Okay. I mean, you interpolate the curve using some positions, control points. In finite element also you do the same, but you don't use the information of the control points. You go to hypermesh or some FE software, you mesh, then it create nodes on those locations. Internally, it also uses that information of that control points. Where is that surface? I should place the node there. Right. But here it's not required.
Thank you, sir. Thank you.
And the second challenge is how do you couple multiple patches? I told patches, like how do you couple multiple patches? That's a big challenge. Multi-patch simulations.
Right. Thank you very much, sir.
Thank you.
Any more questions? Thanks a lot, sir.
Thank you.
Thank you.
We extend our heartfelt thanks to Professor Dr. Sachin Singh Gautam for delivering such an inspiring and knowledgeable presentation. Your insights and expertise have greatly enriched our understanding.
We would also like to express our sincere gratitude to Dr. Ravi Kumar sir for their exceptional efforts for conducting today's session. Your contribution has been immensely invaluable to the success of this event.
Now I would request Dr. Ravi Kumar sir and Dr. Pushpendra Rathore sir to felicitate our plenary speaker. Can we have a round of applause, please?
Okay, thank you very much for attending this session and listening all the three sessions. So now we will move to lunch at their respected venue, guests and students. After lunch, all the paper presenters will have to present at E2 auditorium. Okay, so please be there, paste your poster, and I'll request session chair to be there. I'll give the sheet to the session chair to evaluate the poster presenters over there. So this activity will be done after the lunch. So please, now we can move to the lunch. Thank you very much.
Speakers will have their lunch at F2 lounge. Sorry, sir. F2 lounge, and the presenters will have it in F2 foyer.